this morning. Sorry, the first section in this morning. But before we begin, let me remind the speakers to send their PDF file, the talk slides to the Secretary General, and also let us be reminded that the colloquium this afternoon by Professor Wen is going to start at 20 past 2 instead of 30 past, half past 2 as indicated in the program. It will start 10 minutes early. And also, the location of the talk is in the physics department, not here. So please be aware of that. So without further ado, let us welcome Brian to give us the last lecture of this series. Thank you.
All right, thanks very much for coming back, getting up early. So today, in the talk, I'm going to discuss two separate subjects. The first half, roughly, will be a discussion of a certain class, an infinite class of gapless states. And I'll tell you, I'll be very specific in a moment. And I'll show that this infinite class of gapless states are S-source fixed points, and really they're S equals to 1. And then the final part of the talk will be a kind of more speculative or conjectural discussion of where we think this is going and what it's interesting for, and so on and so forth. Okay, so first, what did we do last time? Remember, I introduced this overarching concept of an S-source RG in terms of a sequence of wave functions, and I said this sequence of wave functions is an S-source RG fixed point if you can take a certain number S copies of the wave function at a certain size and turn it into a wave function at a larger size. Okay, so this is a property of quantum states. It doesn't refer to a Hamiltonian or necessarily. But then I showed you that for a very large class of gapped phases of matter, they are indeed S-source fixed points with S typically either equal to 0 or 1. Okay, and I also talked a little bit about the definition of short-range entanglement, which is sort of talking about the borderline case between S equals 0 and S equals 1. So things that aren't really topological, but like an inter-quantum Hall effect. So what I'm going to talk about in the first part of today is what I call square root states. And I'm going to define them, I'll give you some examples, and then I'll just run through actually, I think, fairly simple argument that given a classical renormalization group fixed points, you'll see that the reason why classical is important is because it enters in the definition of the square root state. Given such a classical fixed point, I can construct a quantum fixed point. And the goal of this part is to explain that construction to you. Okay. So one more time, just to beat it into your heads, here's the definition again, but this time in equations instead of pictures. So we have a family of states, psi L, labeled by system size. And we say that this family is an S-source fixed point if given such a state on an L by L by L torus, d dimensions, I can turn it into a state on a 2L and so on by 2L torus. And the way the construction works is I take S copies of that state on the L by L torus. I put them together. I append some product degrees of freedom here, however many I need. This 2 to the d minus s is just the total number of sites that are not accounted for by the sites of these tori. I take these things, I mix them up with a local unitary transformation, which in principle can depend on the system size, and out has to come the systems, the state of the larger system. So that again is the definition. And so this all-important parameter s is telling me how many states I need to insert. S equals 0 means I can create the state from nothing in a single step. S equals 1 means I need the state of a smaller size and I can blow it up. S equals 2 means I need 2 copies. And so far everything we've encountered has been S equals to 0 or 1. So finally today we'll see some S greater than 1, but not in the first part. So now, yeah.
Is that UL still built out of quasi-local?
Yeah, UL is quasi-local, yeah, absolutely. Yeah, if I let U be anything, this equation has no content because every state can be represented every other state with a unitary. So without further ado, here's the definition of a square root state. The input is some classical data. So first I pick a set of classical configurations, which which I call sigma. So just think about classical Ising spins or something like that. 0 and 1, up or down, whatever. I pick a classical action, or really think about it as a classical statistical weight, beta h. And then I have a classical partition function, which is just the sum over all spin configurations of this e to the minus beta h. So this is classical statistical mechanics. Then given this classical data, I can construct a quantum system as follows. I just declare that there exists a Hilbert space with a basis labeled by one state for each classical configuration. So that's the standard sort of rule. And then I construct a quantum state, psi, which is defined by the following rule. I take psi and I look for its amplitude in this sigma basis, and the amplitude is simply the square root of the classical statistical weight. So that's why I call it a square root state. So essentially the input is I pick a classical statistical model, I make a wave function where the amplitude is the square root of the classical statistical weight. And in fact, you can generalize this, but let me not, let's just focus on this particular case. You could make this action an Ising if you wanted. You could do various additional things. But let's just stick with this simplest classical situation. And I want to point out there's a very large literature on this kind of state from many different directions. For example, in the context of dimer models, they're very important. Also, in the context of tensor networks, you can easily show that such states always have PEPs representation, an exact PEPs, or exact tensor network with finite bond dimension. So they have nice properties from a variety of points of view. What I want to do today is show you that these states are interesting because they can be gapless and because they're s equals to 1. Okay, so that's what we're going to do. So first, let me just say why are these states gapless? Why can't it be gapless? So let's imagine you have an Ising spin example. So I just have spin up and spin down, classical spin up and spin down. That's my basis on every site. And I form this state where H is some spin Hamiltonian, some classical spin Hamiltonian. And then what I call the diagonal correlations, that if I take this operator Z, the quantum operator whose eigenvalue is sigma, if I ask about the correlations of Z at different sites, then it reduces to the classical statistical correlation. That's one reason why these things are interesting. So it's a quantum state whose correlations of certain operators reduce to classical statistical correlation in the same spatial dimension. However, the non-diagonal correlators, that is, things that flip the spins, are not classically, they're not an obvious classical quantity. They may have some meaning in the classical theory, perhaps in terms of dynamics, for example, but they're not simply a static classical correlation function. And so in particular, if the classical model, this beta h, were tuned to a critical point, a classical critical point, then this correlation function would be long-ranged, or some other correlation function would be long-ranged. And so that means that this quantum state has long-range correlations, parallel decaying correlations, and hence it cannot come from a gap Hamiltonian. So if there is a Hamiltonian for which this is the ground state, and I haven't shown you that there is yet, although I will shortly, if there is a Hamiltonian, it can't have an energy gap.
So you will have to correlate long-range large depending on beta, right?
Yeah.
So you choose a particular beta?
Yeah, I choose, just think of beta h as a combined object that I tune to the critical point. So yeah, exactly. I choose whatever beta equals whatever it is for the 2D Ising model, for example. 2D classical Ising model. And then I put that in here as my quantum state, and that quantum state has long-range correlations. Okay, so these wave functions, they're simple to describe, but they can encode long-range correlations. So they're an interesting sort of halfway point between, let's say, the more complicated case of conformal field theory and the simpler case of a gap system. Okay, so here's a first example, just to warm things up. Suppose now that I have a bunch of particles, or a bunch of sites arranged in a line, and the states, the classical states, are either 0 or 1. And then I specify that the weight, the statistical weight, is just a product of delta functions. So it just says that every spin wants to be equal to its neighboring spin. Right, that's a perfectly valid statistical weight. It's a sum of local terms where I just say there's infinite energy cost if they're different, and no cost if they're the same. That's a perfectly valid statistical weight. then the resulting quantum state that you obtain, the resulting squared state, is simply this cat state. 0, 0, 0, 0, 0, plus 1, 1, 1, 1. That's completely trivial. But then we can ask, okay, does this cat state, does it have, is it an S source fixed point? Because we know this cat state is the ground state of a local Hamiltonian, right? It's the ground state of ferromagnetic Ising model in a limit of no transverse field, or a very small transverse field. And in fact it is. And the way to see that is to introduce this unitary, which I call the copy unitary. And this job is to just take whatever value is in the first slot and copy to the second slot when the second slot is initially put into 0. And this doesn't violate no cloning because I'm copying a particular basis. I'm not copying arbitrary state, I'm only copying in this diagonal basis. So if you put in 0, 0 and apply a copy, you get 0, 0. If you put in 1, 0 and apply a copy, you get 1, 1. So this unitary exists, it's well defined. Its action is only partially specified by this equation, but I can fill in the other entries however I want. And then you can easily see that if I give you the cat state on size L plus a bunch of zeros, I can apply L copies of the copy unitary to produce the cat state on larger size. And that works just by taking, imagine every black state again supports the cat state, and the blue states are an product. All I do is I go in locally and I copy the state of the black site onto the blue site for every neighbor. Okay. And that will trivially have the property that it takes the cat state of size L and turns it into the cat state of size 2L. Okay, so in fact the cat state is an S equal to 1 fixed point. Yeah?
Yeah, a cat state is almost just a direct product state.
Yeah, it's almost a direct product state.
And for direct product state, S equals 0.
Indeed.
And this tiny change will make S equal 1.
Yes. It's quite fascinating. This is a general feature of these schemes, is that if you take the superposition principle of quantum mechanics does not play well with these constructions, which is.
I'm worried that another cat state is in the same phase as a direct product state.
Well, it depends on what you mean. I mean, this cat state,
If I take a thermodynamic limit, the cat state is in the same phase as a direct product state.
well, I'm not sure I completely agree with that statement.
Well,
I mean, it has completely different correlations. Like, it has long-range correlations.
yeah, but direct product state 0, 0 also have the same long-range correlation.
No, it doesn't.
Well, it's an Ising model, right?
No, it has different correlations, right? There's no, like, it doesn't have cluster decomposition anymore. Right, so I'm saying there's some difference in the long-range structure.
No, but it's the same phase, right? I mean, if you take a just try to figure Ising model.
Yeah.
If I take a thermodynamic limit, I know the cat state is going to be degenerated.
Yeah.
With all the polarized states
Sure.
in the same phase.
Sure.
But S equals 0 and S equals 1, these two numbers are within the same phase.
Yes.
The same phase gives you two different numbers.
Well, it's just saying that within this phase, there's a degenerate manifold, and depending on what ground state you choose in that manifold, you can give different S.
Yeah, so people wonder how universal the S is. So in the same phase, give you two different S.
Well, I think this is a very special case where you have, well, because you have this degenerate manifold which is locally distinguishable. If I had a unique ground state, this problem would not have arisen. Or if I had ground states that were locally indistinguishable. I mean, I see what you're worrying about, but I don't have a complete statement to make, but I think you shouldn't worry about it.
Does the S depends on the phase? Is a property of the phase, or
it's a property of the state, of the family of states you choose.
So you could be in the same phase of the matter, but be having different.
Yeah, if you have many different ground states, and you want to look at some weird sequence of ground states, then in principle, as this example shows, you could get different values of S for different choices of the ground state.
But that's not the case for topological.
Yeah, for topological, this doesn't happen. Yeah. So the cat state is special in this regard, I would argue. But let me just say, let me not give an argument. Let me just say I don't know of any other case where this occurs. So in that case, it seems pretty universal. Yeah.
When you say you can't distinguish, it is not a problem for topological phase. Is it because the states are not locally distinguishable?
That's right. Yeah, precisely. Yeah, see, everything's local here. So if I have two topological states and I superpose them, then the same operation does the same thing locally because they're all the same locally. Whereas here it's not true. This local operation has a very different impact. Okay, so we can worry about this, but I don't want to. We can worry about it later.
But you start with different states, right? The same local operation. If you start with 0, not cast them, then you get the ground state.
Sure. Yeah. You can certainly choose just all zeros and do.
But that's not due to the local operation. It's due to the C state you start, cat L or product 0.
Well, yeah. Well, just say this unitary. The unitary you can choose in that case is just identity. It doesn't do anything.
But you could also copy.
You could also copy. That's right. Yeah. Absolutely. Okay. And another example of this class, a field theory example, is the so-called Lifshitz theory. This is constructed in very similar fashion. I take a statistical weight, so I think about a two-dimensional field theory, so a scalar field with standard quadratic term. I treat this field theory as a Euclidean quantum field theory and treat it as a statistical system. Then I can form a quantum wave functional psi of phi, which is again just the square root of this thing. And in this case, we actually know a nice Hamiltonian or a nice Lagrangian for which this is the ground state again. And that's simply this Lifshitz theory, where you take the sort of canonical dt phi, but you also have this half functional derivative of the statistical weight with respect to phi. So in fact, this is a more general formula. You can actually take any statistical weight you want here. You can add interactions, and this would still be a Lagrangian whose exact ground state wave functional is e to the minus w over 2. Okay. So now let me go on at last to the example that I'm going to discuss in more detail, which is the statistical Ising model. And in particular, I'm going to study the Ising model in a triangular lattice. So imagine you have spins, Ising spins on each of the vertices of this triangular lattice, and they interact with this classical statistical Ising Hamiltonian with some coupling constant J, some energy scale J. And what I'm going to do is I'm going to switch to the domain wall basis just for convenience. It's easier to do it this way. So I interpret the sites of the triangular lattice as the plaquettes of the honeycomb, and then the links on the honeycomb are telling me whether there's a domain wall or not between this spin and this spin. So this is completely standard. And then I can write the statistical weight of the Ising model in this domain wall basis on the honeycomb lattice using a kind of local tensor form, where I multiply together little tensors T, A, B, C, based on whose takes values based on these links, and the entries of this tensor is written here. So for no domain wall, for no domain walls, everywhere you get 1. If you have a domain wall passing through, you get a factor of e to the minus beta h, basically. Okay, so just trust me, you can work it out in your spare time. This tensor, unless I made a typographical error, will reproduce this statistical partition function. Okay, so we're gonna work with this thing, and really we're gonna study the quantum wave function in this domain wall basis, which is defined by this classical action via the square root construction. Okay. And so before I go any further, I want to convince you, first of all, I want to show you a model which has this wave function, this spherical state, as its exact ground state. So here's the model. Actually, I guess this is still written in the original Ising basis. So, okay. The domain wall basis will be important in just a second. But let's go back to the original Ising basis first of all. So the Hamiltonian, H, is a sum of local terms. Each local term has a minus x, so it has a spin flip. And then there is something which looks like the usual kind of Ising interaction, like ZZ. This sum here over R prime is over all the nearest neighbors of R. So it's just all the spins around it, you sum them up, and you couple them to R with some weight. The only difference here is that it's in an exponential. So in fact, there's not just a ZZ, there's also a sort of ZZ squared term and so on. So there's a sequence of terms. They're still local, but you have sort of a number of different kind of local spin-spin interactions. And I claim, this is actually very easy to check, modulo a sign error, which can be problematic, but with the right choice of signs, this Ising wave function is the exact ground state of this Hamiltonian. In fact, this Hamiltonian is rather nice. Every term here, which I call QR, down here, every term is positive. And the Ising state is exactly annihilated by every term. So it's what we call a frustration-free ground state. Furthermore, the Ising state is positive. It has a completely positive amplitude. So you can actually prove a theorem that says this is the unique ground state of this model. It's called the Perron-Frobenius theorem. It's very simple. So this is the unique ground state of this positive energy Hamiltonian in this case. Okay. And this model is nice. It has multiple phases. If beta j is large, which corresponds to a statistical model which is close to its statistical ground state, then the Ising state you get is just this cat state again. And if beta j is small, corresponding to a statistical model which is highly fluctuating, then what you get is a paramagnetic. So this model actually has a phase transition between a ferromagnetic state and a paramagnetic state. We know exactly where the critical point is because we know where the critical point is of the corresponding classical model. Actually, it's a very nice Hamiltonian because it has negative off-diagonal elements, so it actually is amenable to Monte Carlo. You can sort of study this thing to death. But the point is just that it's local, and this Ising state is the exact ground state. And it encodes a transition, a phase transition between a ferromagnetic state and a paramagnetic state. However, that critical point, which is what we're going to think about now, that critical point is not the usual Wilson-Fisher critical point. It's some multi-critical point. Because indeed, the correlation functions of ZZ at the critical point are not those of Wilson-Fisher, they're those of Wilson-Fisher in one less dimension. So actually this critical point has dynamical exponent not equal to 1, and it's exotic critical point. Okay? So that's what we kind of like to solve this critical point. And here's the way we're going to do it. What we're going to do is we're going to use some fact about the classical model, that it has a sort of renormalization group structure, to bootstrap our way into a statement about the renormalization group structure of the corresponding quantum model. And here's what I mean by renormalization group structure. Imagine you had the partition function on this graph, and imagine for some reason that you can rearrange this graph, you can rewire the graph, so that the partition function on this graph is exactly the same as the partition function on this graph. Or you see what I've done is I've taken these legs here and I've reconnected them in a different way, a way which is very familiar to people who think about topological order. Actually, this kind of rewiring maneuver appears in many, many places. And the way it works here, which was, I think, first introduced by Michael Levin and Cody Nave, is that you have some tensors T, which I introduced before, which encode the wave function. And the idea is you take the tensors T here and you relate them to some other tensors S over here that give you the same amplitude. They give you the same partition function. So this is what I mean by rewiring transformation. Everything else is left alone. It's a local transformation, which I just rearrange the lattice locally, and I have some equivalent statistical model that gives me the same total partition function. Okay. So this is, and now I'm going to talk about a particular scheme, which was invented by Michael Levin and Cody Nave, which they called a tensor normalization group. And in particular, I'm going to talk about the TRG fixed point. And the TRG fixed point is defined as follows. You take this first equation, where I switch the T and the T for an S and an S. And I guess I didn't draw a picture of this, but now you have to imagine doing this switch not only here, but also here and here. And so what happens is when you do this switch 3 times, you turn this original 6-sided figure here into this triangle, the hexagon into the triangle. And so now I can contract these internal indices, right? I can do the partition sum over those degrees of freedom. And what comes out is a new tensor, which has only 3 legs. And if that new tensor happens to be equal to T, then I have some kind of fixed point. That's the idea of microencoding. So I start with T, I make S by this rewiring, then I contract everything together, I get back T, that's a fixed point. So let's just say, okay, you can find this fixed point. That's something you can do with the classical model. Now let me suppose I have the fixed point. What does it imply for the quantum model? Well, suppose I have 2 different quantum states defined on these 2 different graphs. So I have 2 different square root states, one coming from this graph and one coming from this graph. And I have a region A where I'm doing the rearrangements, and everywhere else I'm not touching anything. Yeah?
So what's the physical meaning of this point?
So it just means that you can shrink the system and you get the same tensor back. Right, because you see what this is doing, you start with this hexagon and you make it into a triangle and you shrink the triangle to nothing. So it's actually removing degrees of freedom. So it's like a renormalization through fixed points. Good question. Okay, yeah, so imagine you have now the square root states for these 2 different graphs. And these graphs have the property that they're exactly the same everywhere except inside a little region A where I've done some rearrangement. And now I want to conclude that this psi 1 and this psi 2 are related to each other by a local unitary transformation. And the way we do that, one way to do that is very simple. Imagine you trace over region A in both systems. So I just do a partial trace over all the degrees of freedom in region A. What that gives me is the partition function, or the part of the partition function that comes from region A. Because remember when I take this state psi and I do the inner product with itself, I just get square root of weight, I get the total weight, and I sum over the weight. So I get part of the partition function here and part of the partition function here. But I just said that the partition function locally can be deformed. This partition function can be deformed to this one at no cost. They're the equivalent. And so that means that the partial states, the reduced states on the outside world of this system and this system are exactly the same. So I have 2 mixed states, which come from different pure states. They have different purifications. But then there's a simple theorem that says any 2 mixed states which are the same, if they have 2 different purifications, those purifications are related by a unitary transformation on the purifying space. That is the space which you had to trace out. This is the purifying space. And so immediately it follows that there is something, a unitary transformation relates this wave function to this wave function, and the unitary is confined to this region where I did the transformation. Okay, so actually that's actually, in some level, that's the complete proof. Because we did this locally, we can find this unitary everywhere in the lattice, so we can make some kind of coarse graining scheme. We can coarse grain everywhere. These unitaries are guaranteed to exist. And we map the wave function on some size to a smaller size or to a larger size.
Excuse me.
Yeah.
We need to assume that the wave function that we put on the lattice should be some close to manifold.
Some what?
Close to manifold.
Closed
If the system has some boundary, with that partial move that you used here might not be still available.
Well, okay. Let's see. I don't want to totally dismiss worrying about boundaries, but I guess the idea here is this is a local transformation. So as long as I have this local transformation, even if partition function has a boundary somewhere far away, as long as this local identity is true, then this is a valid manipulation.